This is Renato Bonomini from Moviri, and we're starting today's webinar about mastering Java applications capacity. Let's take a look at the agenda for today. We'll be having a small introduction of who we are so that you get familiar with the speaker for today, Stefano and myself, and what Moviri does. Then we'll go through the review of the 2015 CMG Best Paper Award for about 25 minutes, and we hold question and answers at the end of this webinar. Please make your questions through the webinar in the questions chat for GoToWebinar, and we'll try to answer them during the 15 minutes at the end. If there is any question which can be answered quickly, we'll try to answer those during the webinar, but we hold all of the Q&A at the end. And at this point, I would like to introduce the speakers. The paper itself, Stefano Doni is the author, and he will be talking about his experience in Java capacity planning. Stefano is a senior consultant at Moviri and is our lead for the Capacity Management Special Interest Group. He's a true expert in applied performance and capacity modeling, and you can see the passion in how he does this experience in capacity planning. I am myself Renato Bonomini. I lead US field of operations for Moviri, and my background is in digital signal processing, high performance computing, and I've been working in capacity planning space for many years, helping companies in designing capacity management practices and processes. At this point, let's also spend a few words about Moviri itself. We are a data mining, performance optimization services and software company founded in the year 2000 as Neptuni, that was our former name, and we were a spin-off of the Polytechnic of Milan in Italy. For those of you familiar, when we were Neptuni, we had this product called Kaplan, which is now named TrueSight Capacity Optimization. We sold it to BMC Software in back 2010, and at that point we rebranded into Moviri. Our headquarters are in Italy, in Milan indeed. We have global coverage, and we have branches in the US and UK. We also work outside of the performance and availability space with other business units, which are Content-Wise and Clarify. Let's take a look at today's topic. Now, for those of you who are not familiar with CMG, it's a nice opportunity for you to learn more about performance and capacity management. So I invite you to take a look at the CMG website. And this year for the National Conference 2015, Stefano prepared a paper which was awarded Best Paper of the conference. And this paper was about how to keep the predictions on target, lesson learned from a Java enterprise application capacity planning exercise. Now, I would like to suggest that if you want to make questions or if you want to follow on Twitter, we have an hashtag which is called Movinar, and you will see throughout the presentation that we plan on adding additional webinars on this topic and other topics which we call Movinars. And at this point, I will leave the word to Stefano and he will present the paper. Thank you.
Okay, thanks Renato for the introduction. Good afternoon everybody, and thanks you for joining us today. In this webinar, I'm going to show you some lessons we learned during a capacity planning project for one of the largest financial companies in Europe. The customer engaged us to plan the capacity of a business-critical application that was being rolled out to all of its branches across several nations. In doing this capacity planning exercise, we've encountered some interesting challenges in terms of how to properly plan capacity and manage efficiency of Java enterprise applications. To address them, we have developed a set of innovative methodologies that we had the pleasure to present at this year's CMG National Conference in Texas. As Renato was saying, if you don't know CMG, CMG stands for Computer Measurement Group, and it is a not-for-profit worldwide organization of IT professionals committed to sharing information and best practices about capacity and performance management. I've been so lucky to receive the Best Paper Award of this year's conference. I'm not going to share with you the first lesson that we learned during this project, which is how to keep capacity prediction on target with Java enterprise applications. Let's start by describing the problem we need to solve. Suppose you need to estimate if your business-critical service will be able to cope with the increased traffic of your most important business campaign. The stakes are high, you can be wrong, or your business will be severely impacted. How do you make sure there is enough capacity to handle the peak load, such as a 30% increase in number of users on your e-commerce site? As IT departments seek to be more integrated and provide more value to the business, capacity management needs to be able to size capacity over business goals. The real question is, how can you plan the capacity of your IT resources to support a given business volume? Capacity management is the discipline aimed at answering this question. It is a set of processes and methodologies to ensure IT systems have enough capacity to support business initiatives in a cost-effective way. There are two main ways to do capacity management. The first and most common approach is called component capacity management. In it, the utilization of IT resources, such as the CPU of your servers, are collected and forecasted into the future. IT resources could be anything your server needs to run properly, such as CPUs, storage space, and so forth. When the predicted utilization reaches some saturation thresholds, like for example 80%, new capacity is procured. As you can guess, there is a problem with this capacity management approach. Basically, it fails to account for the business dimension. How can you predict how many users or transactions your site can support just by looking at CPU utilization or storage space? You simply cannot estimate your service capacity in business terms just by looking at IT resources. A more comprehensive approach is required. So, how do we estimate how much business our system can actually support? To do that, we need to know a lot more. What is needed is a more mature approach that we call business-oriented capacity management. In it, we create a computer performance model that is able to describe and predict how the performance of the system is related to the amount of business workload the system is managing. We call this a business-oriented capacity model. To create such a model, we need two key inputs. IT utilization metrics, the same ones we use for component capacity management, which is CPU utilization, storage space, memory, and so forth. And we need also an additional input, which are metrics that describe how much work the system is doing in business terms. It can be the number of products sold, the number of users accessing the system, and so forth. We also need thresholds in order to understand the maximum workload the system can support within a desired service level or without breaching a target utilization value, for example, 80% of CPU utilization. Lastly, configuration and service models are also required to understand the architecture and configuration of your application, for example, to distinguish Java application servers from databases, as they are usually modeled differently from a capacity planning perspective. So, what's the purpose of this capacity model? The model is used to predict the performance of the system under different load or configuration conditions. The most valuable output is the maximum business capacity, which means how much business the system can support in its current configuration. Let me show you how a business-oriented capacity model works with a graphical representation. This chart shows a correlation plot among a business KPI on the x-axis, for example the number of users, and the utilization of an IT resource on the y-axis, for example the CPU utilization of your servers. Let's pick a point on this chart. Suppose you measure your system for an hour. During that hour, the system has served 5K users. During the same hour, the system utilization collected from monitoring systems was 30%. We repeat this data collection process until a relevant set of data is collected from the system. Once we have enough data, we can perform statistical analysis in order to identify the capacity model that explains the behavior of the system. The dashed blue line that you can see on the chart is the model that we have derived on this example. Once we have the model, we can do the actual performance prediction. How do we do that? We extrapolate the model up to a given threshold, for example, a target value of utilization, like 70% in this example, and we can predict the business capacity of the system. In this example, we can estimate that the system will support 14K users. This is what we call the maximum business capacity. Once we estimate the maximum business capacity, we can also derive what we call the residual capacity, which is how much headroom do we have with respect with the current workload peaks. In this example, we can estimate that additional 8K users can be supported on this system. What we have seen so far is the best practice in capacity management to develop business-oriented capacity estimations. However, even though you follow these guidelines, if your service you are managing is a Java application, chances are that your capacity estimation will be hugely inaccurate. Why is that? What is the problem with Java applications? The problem is that Java application might suffer from a needle bottleneck, which is not something introduced by bad code, but it is related to fundamental Java principles and therefore lies at the core of every Java application. Java is widely used in business-critical and enterprise applications thanks to the development efficiency, mainly due to automatic memory management. The platform frees the developer to take care of memory management. While this is great for development efficiency, this Java principle brings a set of challenges for the capacity manager. So why Java memory management affects our capacity prediction? Why do we have to bother about it? There are two main important facts about Java memory management that you need to be aware of. All the Java memory required for your application to run gets allocated into a fixed memory region called Java Heap. The size of the Java Heap region in memory is fixed. The second point is what happens when Java Heap memory is exhausted. A cleaning process called garbage collection kicks in and cleans the garbage, which is memory no longer used by the application. The key point here is that this very cleaning operation might stop your application. Normally, application posts introduced by garbage collection are small and go unnoticed. However, if stress builds up into the heap, the garbage collection can freeze your application for seconds or even tens of seconds, possibly even crashing the entire application if load is excessive. So what is the bottom line? Bottom line is that Java has an additional hidden bottleneck built into the platform, which is a common scalability limit of Java applications. The first visible sign of heap saturation might be a user-facing service disruption with devastating impact on your business. So how does all of this matter to our capacity predictions? Let's look again at the previous chart in which you have predicted the business capacity using standard capacity management models, the gray circle in this chart. If your Java memory becomes a bottleneck and you are not aware of it, the maximal actual business capacity the service can support will be hugely lower. The result is that the business critical service you are managing will crash well before the business volume you have predicted will be reached. This is something we really need to avoid at all costs. As being capacity manager, our success depends on the accuracy of our prediction. So we really need a way to enhance our capacity models in order to be able to predict Java heap saturation issues. But how can we do that? Let me share with you the methodology that we have developed to solve the problem. The idea in itself is pretty simple. Why not including Java heap memory as an additional resource in our capacity models? Capacity models typically include just physical resources of your system, CPU, memory, I/O, and so forth. The idea is, why not extending the model to include a software resource like the Java heap? The first challenge in doing that is to find a good metric to measure how much the Java heap is really used. For CPU resources, we have CPU utilization metric. What do we have for the Java heap? The heap utilization is a widely used metric in Java performance analysis and is often suggested as a metric to be used for forecasting purposes. It simply measures how much of the heap space is used at any given time. Heap utilization is reported by all Java monitoring tools and application performance management solution. The real question for us as a capacity planners is the heap utilization a good metric for business-oriented capacity planning? Can we use the heap utilization to predict how many users our site can actually support? The chart on the right shows a correlation plot of heap utilization against the number of users accessing our system. It turns out that we don't see a straight line that we saw before with the CPU utilization. Something strange is happening here. The heap utilization basically stays flat even though the number of users increases from 50 to 150. So the answer is no. The widely used heap utilization metric used also for forecasting purposes in the Java performance community is not enough to build a business-oriented capacity model, which is our ultimate goal. So, if the available Java memory metrics are no good for capacity planning, what should you use? The key to derive the ultimate Java memory metric for capacity planning is to understand more about what's in the Java heap, what's happening behind the scene. If we could look into the heap utilization, we will discover that the Java heap contains two things. It contains both live data, which is data actively being used by the application, and it contains garbage, which is sort of dead data, which is data no longer in use by the application. The key point here is that the heap utilization stays flat with respect to the workload due to the presence of garbage. We are measuring both live data and garbage. In contrast, the live data represents the real memory footprint of your application and therefore is more likely to be correlated with business KPIs. Therefore, to reach our goal, which is building business-oriented capacity model that can predict how many businesses can actually support our system, we really need to measure live data in isolation. And here comes the real surprise. When we developed this methodology, we discovered that live data is not reported by most Java monitoring tools. Even leading application performance management solutions on the market today don't report it. So how do we measure live data? Luckily, Java comes with a built-in diagnostic facility that is able to provide more detailed information about the internal Java memory management operations. It is called garbage collection log and can be enabled on any JVM vendor and any JVM model on the market today. In this In this slide, you can see an example of a garbage collection log from an Oracle JVM with a specific garbage collection algorithm. The good news here is that we discovered that it is actually possible to calculate live data, which is the real memory footprint of your Java application, directly from garbage collection log information. So the final question is live data a better metric than heap utilization for our purposes? Which means, can live data be actually used to build business-oriented capacity models? In this example, we can see a correlation plot among live data and the number of users. Notice how clearly the live data is correlated with this business driver. Live data is directly proportional to the amount of users accessing the system, which is actually something that we can expect. So the answer is yes. Live data is a good memory KPI to building business-oriented capacity model for Java applications. However, we are not finished yet. There is a second challenge in doing Java business-oriented capacity modeling. How do we estimate how many users our site can support without a threshold for the live data? In other words, how much live data is allowed to grow within the Java heap? For CPU, we commonly use a threshold such as 70% in order to keep the site responsive, to avoid response time elongation. What do we use for live data? Which kind of threshold is good for a capacity planning exercise? The selection of the live data threshold is a trade-off between cost and performance, as usual in capacity management. The chart on the left shows what happens if we set a conservative threshold such as 20%. We are basically wasting capacity. We are not making effective use of the available memory that we have in our Java heap. Conversely, let's look at the chart on the right, which shows what happens if we set a too aggressive threshold. In this case, you can see that the garbage collection is constantly working hard, trying to free some memory. But it can't, as the heap is almost always full with live data, which is data that cannot be free. It is not garbage by definition, so the garbage collection is really not able to free memory, but it is working hard. If you recall the key facts about garbage collection and Java memory management, the results of lot of garbage collection activity is lots of application pauses. Most likely, your user will start seeing service degradation. And even a small workload increase might lead to a complete service disruption. Our suggestion for capacity planning's business-critical application is to start with a threshold of 50%. You might be able to increase the threshold and increase the utilization of your existing capacity if you closely watch the application pause time and you make sure that you are not putting excessive stress on your Java memory. So we are now ready to put together all the lesson that we have seen so far. So the first chart on the left shows the result of our methodology. We can now predict how much business our Java application can actually support. How can we use this capacity model in a real-life capacity planning scenario? An example application of this approach is to perform a right-sizing exercise and determine the optimal number of application server instances that supports your J2E business-oriented service. With the methodology that we have presented, you might be able to determine that your current application server cluster, consisting of 45 application server instances, can support a maximum business capacity of 3.5K users. This is the first valuable output of the model, which is a real visibility into the capacity considering Java bottlenecks. Now you can also use this information for planning purposes. Suppose your marketing department is expecting that 4.5K users will use the application at peak time due to a new business initiative. Do we have capacity to handle that? No, in this case. With the capacity model that you have derived, you can estimate that 60 application service instances will be required, so you need additional 15 instances. So back to our initial question, how can IT provide value to the business? Business-oriented capacity model, especially thanks to the methodology that we have shown you, can actually help the business in two key ways. We can help by avoiding cost, because what we see in organization is that when capacity visibility is not really clear, organizations typically do overspending, so there's more investment that are required to keep the service on. The other key way is to reduce risk of business loss and reputation damages. As we have seen, if we overlook Java capacity bottlenecks, we really run the risk of having unexpected service downtime, even though our capacity prediction was not expecting it. So the recap of the key takeaways is that with this Moviri innovative and award-winning methodology, you can actually start planning capacity of Java application with confidence, finally. The key point I would like to stress here is that component capacity management, so simply trending IT resource utilization, is not enough. You cannot really estimate how many users you can support just by looking at your CPU or memory. Business-oriented capacity planning techniques are the answer. However, they can severely overestimate the business capacity in case of Java application. Java Heap memory is in fact one of the most common bottlenecks causing outages in Java application, and you need really to take that into consideration. Java Heap utilization is a combination of live data and garbage. Live data is what we need because it represents the real memory footprint of the application, and it is the correct KPI to use for capacity planning. Live data, luckily, can be derived from garbage collection logs, even though most monitoring tools and even leading APN solution on the market today does not provide it. We also provided some suggestions in terms of sizing the threshold. So how much memory can we push? How much memory demand can we push? Can we extract out of a JVM instance? And our suggestion for business critical application is to start from 50% and increase from there. I'm now happy to take any question and provide answer to your questions. So feel free to answer questions on the chat and on the question side.
Thank you, Stefano. There are a few questions. So there's one actually that came through registration. So Calvin, a question, which let me play back to you. What method do you use to predict capacity needs? In particular, if the business does not provide current demand or expected future demand.
Okay, this is actually something that usually happens in capacity management. My suggestion is really to build a business-oriented capacity model with the methodology that we have shown, which enables you to get a real visibility of the capacity, the amount of capacity the system can actually support, which is nevertheless a key output of your work. If you don't have capacity forecasting, demand forecasting estimation, what you can do and what I would suggest to do is really to do forecasting on the demand side. So you would like to track the amount of users accessing your system, the amount of transactions performed, and forecast them into the future in order to understand when the maximum capacity that you have predicted will be reached.
Excellent. Thank you. So going to another question, now we have Ted who sent up this question, and for everyone's benefit, I'm putting these in the chat window so that you can read them. Okay, so let me play back that to you. Java live data bottleneck is just another bottleneck that went unconsidered. How do we know we're not missing anything else, like I/O, for example?
Yeah, good question. This is actually where the experience of the capacity planner comes into play. So as a capacity manager, we really need to come up with a good model that is able to represent all the potential bottlenecks of a system. So we really need to be able to know the system in detail, know the technology involved, and build a capacity planning model that is able to consider all the resources that our system is comprised of. So up to now in this exercise, what I showed you is basically how to detect and how to plan for a specific bottleneck, which is a Java bottleneck that is typically not considered. But what you can really do and should really do is to come up with a model that considers basically all the potential bottlenecks. And typically capacity management tools allows you to do that, to build a capacity management model that is able to consider more than one resource. Which one to select is really based on the experience on the capacity planner and can be actually understood by performing a performance analysis on the system in order to understand how the system is currently behaving, what are the likely bottlenecks among all the different physical resources the system is comprised of.
Excellent, thank you. Now we have a couple of questions, one from Ben. Hi Ben, by the way, and one from Jorge. Hi Jorge, which are pretty much similar. So let me just consolidate the two questions. So Ben has a question about what was the parameter in the garbage collection log that indicates live data size? And to that purpose, Jorge was asking, how did you get that information out of this GC log? And did you use a standard BCO ETL? How did you get that out?
Okay. So in terms of which specific information to look for into the garbage collection log to derive the live data, that's really dependent on the specific implementation of the JVM. So in the example I shown you, I presented you a garbage collection log taken from an Oracle JVM using a concurrent market sweep algorithm, which is a specific garbage collection algorithm. By the way, the output of the format of the garbage collection log is also depending on the specific garbage collection algorithm. So the answer is really depends on which specific algorithm is being used into the specific JVM or application service. For example, for the concurrent market sweep garbage collection, what you really need to look at is the amount of memory that is live, that is used after a garbage collection process. So by isolating just the garbage collection line that shows you the amount of memory that is live after a garbage collection, you will be able to actually capture the live data size. As regard the other question, basically you have a number of options in terms of how do you specifically implement that on your capacity management tool. Speaking about BCO, basically you can actually develop a custom ETL that is able to parse garbage collection log. And by the way, as I was saying, you need to look at specific fields, do specific calculation based on your JVM implementation. So it's not simply a parser of the log file. You can also find use for other ways, such as using some log collection tools, log analysis tools, such as Splunk, to consolidate all your logs and to gather information from a single data source for your BCO instance.
Thank you, Stefano. We still have about 5 minutes left for Q&A, and they keep flowing. So next question, which I put again in the chat. Does it require to collect manually each single garbage collection log for every JVM? And from another point of view, a very common question, we will experience overheads turning on garbage collection log.
Okay, good question. So in terms of overhead, the good news is that there's really no measurable overhead in turning on garbage collection. We also got this question, of course, from the customer when we told them to really turn on garbage collection on all their application servers. Oracle even recommends it to turning on even on applications, production application servers, because there's really no overhead, there's no tracing involved, no profiling or whatsoever. What the JVM has to do is really to print out statistical information every time a garbage collection operation is done. So it is not something that is being done 1,000 times per second. So there's really no overhead involved. And by the way, we also measure it against by comparing an application server instance with garbage collection turned on and another one with the same identical workloads and with the garbage collection turned off, and we really didn't see any difference.
Okay, good. I have another good question. Let me just copy and paste it for everyone. Okay, why wouldn't you increase the memory of the JVM instead of building out another JVM? Good question.
Yeah, very good. Okay, you can do both actually. This comes down to basically the preference of the customer, of the operation team, of your architecture blueprints. The customer we worked on really preferred to use standard JVM size, I don't know, 6 gig of Heap, because it was more confident that this kind of JVM memory size was good for the workload. You can actually improve the capacity of your JVM by increasing the heap size, which is something that we also suggested, because another point is that the live data size, you have a pretty high live data size overhead even with almost no workload, because this is due to the application server classes, all the caching that are live even though you are not serving any user. So you have a sort of fixed utilization value irrespective of how many workload, how many users the system is really supporting. So if you are just adding a high number of small instances, you are basically paying twice and much more times this kind of overhead with respect to having a small number of instances with much higher heap size. The downside of increasing the heap size is that the garbage collection can actually introduce more lengthy pauses, because as more heap has to be cleaned, there are times where the garbage collection might take more time to do the cleaning. So you have to be a little bit careful also in extending the heap size, even though it might provide you benefits in terms of reduction of the number of instances.
Excellent, thank you. So we have one last question. Let me again paste it. How do memory leaks fit in this picture?
Yeah, that's great question, because we actually have an additional lesson on the paper on this topic. Basically, this methodology allows you to also anticipate memory leaks with a model-based approach, because when you build such a correlation between live data, the memory footprint, and your number of users, you are actually able to understand, in case of new application releases, if the developers introduced a regression. So if you suddenly see that the pattern of growth of the live data size with respect to the number of users is changing, and in particular you might see some flat behavior in which you will have a live data size that is flat irrespective of the number of users, this is a clear indication that a memory leak is going on. So this kind of model is very good also in terms of identifying and predicting memory leaks before they introduce outages into application services.
Okay, thank you. So we are right about the time that we ask for everyone's attention today, and thank you. So I would like to thank you everyone for joining today. And as you might have found out, we call these Movinars. So if there's any other question that you have and this webinar is over, and if you have colleagues who were not able to attend, we are be recording this webinar. It will be made available online for you to join later. And we also have a series of webinars on this and other topics that we're planning. The paper that Stefano presented at CMG had a lot more information, which we couldn't just do in one webinar. So we'll send out invitations for other follow-up topics, in particular that are all around garbage collection and all about what is Java capacity planning. If you have any question, just follow up even on Twitter with Movinar, send them to me, marketing. And thank you everyone for attending, and hope that everyone comes back again at the next webinar.
Thank you.